All right, we are continuing with combinational components. We started with the decoder. We did the multiplexer. There's still a few things that need to be done with the multiplexer. And then we go into another combinational component. Let's, before doing the components, or continuing with multiplexer, there was something that I missed last time. See the S here, if you're doing multiple multiplexer, parallel multiplexers, all the S inputs are the same. So here is a 2-to-1 multiplexer that is repeated 3 times. Here is a 2-to-1 multiplexer that is repeated 8 times. They all receive the same S. Now, if there is a 4-to-1 multiplexer, okay, something like this, and then there are these 4-to-1 multiplexers are again repeated 8 times. A, B, C, D, each of them 8 times. Then the S1, S0, so these are really 8 4-to-1 multiplexers, and then they all have S1, S0. The S1 and S0 are connected to all of them, just like the single S that is connected to all of them. The S1, S0 is also connected to all of them. So that's something that I think I missed saying that. And now let's go on with the multiplexer. See, what we promised with the multiplexer was we talk about functionality, gate level hardware, cascading, which we did. Configurability, there is really not much configurability in multiplexers. Cascading you do, and that's it. Verilog description we did. We're gonna revisit Verilog description later on again. The application for selection, for serialization, and all that. But then there is something else that we did not finish, and that was using the multiplexer for random logic, or actually the MUX-based design, which I'm going to continue with that now. And then we go on to the next one. So let's talk about multiplexer-based design. See, this is the thing. Multiplexers can be used for almost any logic that you want to implement. Okay, any circuit can be implemented with multiplexers. That's why in FPGAs, some of them have arrays of multiplexers for implementing whatever logic you want on the FPGA. And so I can take a multiplexer and build something. If I have a very random Carnot map, let's, for example, let's go back to the previous slide. Let's say I have a Carnot map which looks like this, looks very crazy, and A, B, C, D, 0, 0, 0, 1, 1, 1, 1, 0. Okay, it's a 4-variable Carnot map. Then you say, let's say there are ones here, there are ones that there is no way you can map them together. There are ones that are spread all over the place. Okay, and this is really not that bad, but anyway, it's just a 4-variable Carnot map. And so you say, well, if I want to do this, I have to use a Carnot map. Maybe I can map this, maybe I can do this, 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 and that's all really all there is to it. And then you write the expressions. That becomes A, B, C bar, or with A bar, B bar, A bar, B bar, C bar, D, or with A, B bar, C, D, or with A, B bar, CD bar, okay? Let's say my expression becomes this. Then you look at this, you say, well, what do I do with this? This is four product terms, and these four product terms, they are these four product terms are AND gates, right? Trying to do the Carnot map. There is an OR gate here. It doesn't look very pretty piece of hardware. And so you say A connects here, B connects here, C bar connects here, and on and on. All right? And perhaps you can do a little bit of factoring with some of them and make it look a little bit better, but then that's all there is to it. So what I'm going to say is, and then let's also say something else. Then I look at this and I say, yeah, this is not a package I have seen. It's not decoded. It's not a package. Let's say it's not a comparator that we will see later on. It's not an adder or anything like that. And therefore, I'm stuck with this random logic that doesn't look so great. Something you can do is implement this using multiplexers. So the whole thing, instead of having discrete logic, little pieces of logic all over the place, instead of doing this, you can have a multiplexer to implement this completely. We're going to come back to this. All right. So that's the subject I'm discussing now. Let's say I'm given two 3-variable Carnot maps, okay? Two 3-variable Carnot maps. These are C, O, and S. We will later on know what these are. And there are ones here and then the zeros everywhere, right? So what I do is I take this 3-variable Carnot map, the one on the left-hand side. The variables, the vertical variables are A and B, and this one, the same thing. So I say this. Let's read the Carnot map. Isn't it that when AB is 0, 0, I'm going to be sending 0 through whether C is 0 or C is 1. Okay, I'm reading my Carnot map differently. I'm not reading my Carnot map based on prime implicants or implicants. I'm reading my Carnot map based on the columns. There are 4 columns in this Carnot map. So let's look at another one. If AB is 0, 1, for the upper map, if C is 0, I'm sending a 0 out. If C is 1, I'm sending a 1 out. What it means is I'm sending C out. How about the other one? The other one, this one, in the second column, if C is 0, Carnot map value is 1. If C is 1, Carnot map value is 0. And therefore, this column becomes C bar, complement of C. All right, so this is what I'm going to do. I'm going to, for each of these Carnot maps, I'm going to have a multiplexer and make the multiplexer so that the inputs of the multiplexer correspond to the columns of the Carnot map. Since there are 4 columns, I need 4 inputs for the multiplexer. Since there are 4 inputs for the multiplexer, I need a 4-to-1 multiplexer. A 4-to-1 multiplexer requires 2 select inputs. 2 select inputs become S1 and S0. In order to make the multiplexers correspond to the columns of the Carnot map, what I do, I connect the same way AB is a binary number with A being most significant, B being least significant bit of it. I connect A and B in this exact order to the select inputs of the multiplexers. 1 multiplexer for the upper map, 1 multiplexer for the lower map. Okay? When this happens, then I say when AB is 0, 0, on one side, on the left side, on the Carnot map side, if it is 0, 0. On the Carnot map side, I'm selecting the 0, 0 column, which is the yellow column, which is what? Which is 0. Okay? Whether C is 0 or C is 1, this is 0. And therefore, I put a 0 here. Let's go on to the next column. The next column says 0, 1, AB 0, 1. That means row number 1 of the multiplexer. One of the multiplexer. Look at the green circle I'm showing on the left. If C is 0, that contents of the Carnot map is 0. If C is 1, that is 1. And therefore, what goes in there is C, or C in. Okay? The next one, remember the next one, when we get to Carnot map, we have to skip. The next one is 1, 0, row 1, 0, row 1, 0. Now let's look at that. Well, that turns out to be C in again. And then finally, the fourth one, which is this, 1, 1. Whether C in is 0 or 1, the input here is 1, and therefore you have a 1 here. Let's do the same thing for the lower Carnot map. The lower Carnot map, the last one, 1, 1 is just C in, and then the first one is for the okay, that has to be C in. Okay, this is CI. Okay, notice that I have for 0, 0, the for the 0, 0 column. For the 0, 0 column, CI being 0, the Carnot map is 0, CI 1, the Carnot map is 1, and therefore CI connects to this. The next one, that is the green column. This is the complement of CI. The orange one is this one here. That again is complement of CI. CI 0, this is 1. CI 1, this is 0. That means complement of CI connects to this. So what did I do? Well, without having any extra logic whatsoever, I used two multiplexers, and these two multiplexers were used to implement the Carnot maps there. See, this is 0, 1, 2, 3, 0, 1, 2, 3. Just to mark these properly, 1, 0, 1, 0 for the most significant and the least significant bit of the multiplexer select inputs. And so what did I do? I took a 3-variable Carnot map, and I said that I can leave one variable for the side or for the inputs, and therefore the only choices I will have for the inputs will be either 0 or 1 or that variable or the complement of that variable. Okay, that leaves me with 2 more variables. For a 3-variable Carnot map, that leaves me with 2 more variables. Well, 2 more variables, it means that I need a 4-to-1 multiplexer, and therefore I was able to completely implement this 3-variable Carnot map with only multiplexers. This circuit turns out to be an adder, which we will be seeing later on. Okay, what if I have a Carnot map, a 4-variable Carnot map, or something like what I started with today? This is a 4-variable Carnot map, okay, 4 variables, and if I want to see it here, 4 variables. What I want to do, I only want to leave one variable for the inputs. That one variable will either be 0 or a 1, or that variable of these 4 variables of the Carnot map, or the complement of that. This way, I don't have any logic on the side of my multiplexer. Leaving one variable for the side or for the inputs. Okay. Again, 4 choices with one variable, 4 choices for the inputs of the multiplexer, 0, 1, that variable, and the complement of that. That leaves me with 3 variables. With 3 variables, then what do I need? 3 variables need to connect to the select inputs. For the 3 variables to connect to the select inputs, I have to have a multiplexer that has 3 select inputs. That means an 8-to-1 multiplexer, and therefore for implementation of this 4 variable Carnot map without using any extra logic except inverters. On the outside of the multiplexer, I need an 8-to-1 multiplexer. Okay, let's see what the arrangement of the variables are. I'm gonna cut my Carnot map in the middle, half up, half down. Okay, and then I'm gonna cut. I've already decided I have a 4 variable. I have an 8-to-1 multiplexer, right? And then I'm gonna cut my multiplexer half up, half down. I'm gonna associate the upper part of the Carnot map with the upper part of the multiplexer, the lower part of the Carnot map with the lower part of the multiplexer. Okay, let's look at the variables. For the upper part of the Carnot map, C is 0. Okay? For the lower part of the Carnot map, C is 1. What did I say? I said I'm going to select the upper part of the multiplexer for the upper part of Carnot map. And therefore, if this is the case, I'm going to connect my C input. I'm going to put my C input okay, right over here. If this happens, look, C0 and AB, whatever they are, that means 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Okay? That makes that upper map correspond to the upper part of the Carnot map. How about the lower part? The lower part, again, this is 1, and therefore, okay, C1, that means 1, 0, 0, 4, 5, 6, and 7. Okay, so now let's look at it like the problem we had here. 2 Carnot maps, okay, except that now we have these 2 Carnot maps kind of joined together. And AB are selecting either the input 0, 1, 2, 3 of the upper map, upper part of the upper part of the multiplexer, or AB are selecting the 4, 5, 6, 7 input of the lower part of the multiplexer, depending on C. So with C, I don't have to worry anymore. I'm gonna put A and B to the other 2 inputs of the Carnot map. Okay, once I do that, okay, so this is bit number 2, 1, 0. Once I do that, then correspondence of the columns becomes as such. Okay, let me do this. This corresponds to this. This corresponds to this. Okay. This corresponds to this. This corresponds to this. This corresponds to this. This to this. And finally, this to this, this to this. Okay? And then I split the Carnot map as such. This is for C equal to 0. This is for C equal to 1. So let's do the mapping. Let's look at the first part, the upper part. AB00, 0, I have ones all over. Okay, that means whether D is 0 or 1, the only variable remains, that variable that I'm going to put for my data inputs becomes only D. If AB are 0, 0, then the output is going to be 1 no matter what for the upper map. Okay, I'm doing the upper map first. And therefore, I put a 1 here. Next column, 0, 1, complement of D. D is 0. This is 1, D 1, this is 0, complement. Next column, which I did wrong. One is the third one. Remember, we always reverse the third column and third row of the Carnot maps. Okay. So continuing, then now I'm looking at the 1, 0 column, the orange column, or column number 2. That becomes 1, 0. That means D bar. Okay. And finally, column number 3 of the upper map, 0, 1 is the same as D, and therefore D goes here. For the lower map, I have 0. I have D bar. I have 1, all ones, and I have D, and therefore 0, D bar, all ones, and D go there. All right. So what I've done is I have turned a 4-variable map into a single multiplexer, no logic on the outside whatsoever. What if I have a 5-variable map? Okay, I need only 1 variable to use for the data input, and therefore that leaves me with 4 more variables. Okay, and therefore what I do is I use one of the variables for the inputs, and therefore I need 16 to 1 multiplexer. All right, so let's go up here. If I were to do this using a Carnot map, just quickly, just as another example. 1, 2, 3, 4, 5, 6, 7, 8. CAB, okay? And then 0, 1, 2, 3, 4, 5, 6, 7. Okay? This becomes D. Next one becomes 0. Next one becomes 0. This. 0, 0. Next one becomes 1. The lower one, this one is 0. This one is D bar. Okay, next one is D, and next one is 0. See? A big difference between the discrete logic here and the single multiplexer for implementing this Carnot. All right. Like I said, we can do 5 variables if we want, and things will be a little bit more numbers, but then it's not as difficult as you do with Carnot maps, where you have to do the mapping, you have to look for 5 variables, the right map, the left map, and all of this. All right, I'm going to do one more little circuit here, that is parity circuit. And a parity circuit is used for error correction. Look, for example, you have 8 lines, 7 lines, 7 data lines going from one place to the other. Okay? you want to have a duplication, or you want to duplicate the information that goes from one side to the other. Okay, one way of duplicating it is to have all these 8 lines repeated. But you don't really want to do that, because that means a lot of hardware that you have to repeat. The reason you want to do the duplication is because if noise happens along the way, you'll be able to at least detect it. Not necessarily correct it, but at least detect it. So what you do is you put a function here that is a function of all these 7 inputs. Okay? And as you are sending your data, as the 8th data, you will also send the function that you generated. When it gets to the right-hand side, what you do is you recreate that same function. This is that function. You recreate that same function. Okay? And then you also have the function sent as the 8th line in your transmission. And therefore, what you do is you compare the 8th line with the function that you created. If they are the same, you are fine. If they are not the same, something has happened. I'm not going to say what has happened. I know an error has happened. Or maybe one of these lines is, or the function is, because my function only takes 7 lines and just creates 1 line. Maybe the function has been changed so that, or the lines have been noised so that even though the inputs are different, but then what you have sent and what you receive are different, but still the function hasn't changed. But that doesn't matter. Okay, what I'm going to do is I'm going to create that function. The function is as simple as this. I count the number of ones on the input side. This is the input side. This is the output side. I count the number of ones on the input side. And if they are odd, my function creates a 1. And then I send it over to the next side. The next side, I take the 7 lines again and then recreate the odd even thing. If they're odd, then I say, what? This is odd. On the sending side, it was odd, so it looks okay. That doesn't tell you that definitely there has been no noise. Because you have 1 0 0 1 0 0 1 1 2 3 4. Okay, here the number of ones are odd. You are sending it over, and then it turns out this becomes 0, this becomes 1, this becomes 1, this becomes 1 0 0 0. Okay, the number of ones are odd. The number of ones on the receiving side are also odd. Then your circuit tells you everything is fine, which is not. Okay? But that doesn't matter, because if there is noise in your transmission, there will be many other data sets that pass through this noisy line that if your odd function, which we refer to as odd parity circuit, doesn't detect one set of data, the next set of data is not detected, but then eventually, because of all the inputs that are going from one side to the other, sooner or later it will be detected. This is called a parity circuit. And if you keep the number of ones as odd, this is odd parity or even parity. And then the compare. Let's look at compare. A, B, 0, 0, 0, 1, 1, 0, 1, 1. Okay, let's say equal. This becomes 1. Okay. An equal circuit is nothing but an XNOR circuit. What it means is not equal, NE, is XOR. And therefore, the error flag is this one over here. You put an XOR there. How about the odd circuit? Well, the odd circuit is also a XOR circuit. So what you do is, on the left side, you create the odd. On the right side, you create the odd. And then you put an XOR for comparing them. So you will have an array of XORs on the left-hand side and an array of the XORs on the right-hand side. How do we arrange these? Well, look what I have here. For a 4-input case, I have I0, I1, I2, I3. This is one way of XORing it. And then this is another way of XORing it. The one on the left is preferable. Why? Because they both do the same exact thing. They both form XOR of I0 and I0 XOR I1 XOR I2 XOR I3. They all form the same function. They both form the same function, but the one on the right has 3 logic levels, 3 XOR layers. The one on the left only has 2. Okay, so the tree structure on the left hand side is a better one than the one on the right hand side. And this is called odd parity circuit or even parity circuit. All right, then we go on to the next one, comparators.